Welcome back to our Excel template calculation demonstration. So this is a follow-up of our module 2. So we are going to consider a fully restrained beam of 8 meter span. Then the top flange is fully restrained with a concrete slab, fully crowded and covered with structural strip. Then the bay width is about 2.875. This we have to consider this. Then we are going to consider the following check: the bending moment resistance check. We will also look at the shear resistance check. Then we will consider the serviceability, which has to do with the deflection. So let's quickly go to the Excel template. Okay, so this is the Excel template. This is where we perform the loading. We will also design our simply supported fully restrained beam. So the beam span length is 8 meter, then the bay width is 2.875, 2.875 meter. Then we look at the loading. The first thing when you are doing any design is your ability to be able to capture the accurate loading on that structure. So the loading will determine the bending moment, the shear force. So if the loading is incorrect, it means that every other information or every other result that you will have will also be incorrect because the bending moment is dependent on the load, and even the shear force also is is also uh, dependent on the load. So we look at the save weight of the beam. So we assume the save weight of this beam to be 0.1, then the services to 0.3. Then we look at the 120 light weight concrete on profile metal deck. Now remember that we are designing this beam. So we are designing this beam. And I think let me quickly show something here. Let me quickly show you something so you have an understanding of what we mean. So this is the metal deck. This is the metal deck. This is the metal deck, the steel profile sheeting. So this is the metal deck that is constituting the load. So let me look at this beam. Let me look at this beam. These are the primary beam. I'm looking for where I have the secondary beam. Okay, this is where I have the secondary beam. This is where I have the secondary beam. Okay, so this is where I have the secondary beam. So this is the beam that we are going to design right now, and it is carrying this metal deck. Okay. So the overall thickness of the concrete is 130. Is 130 overall thickness. So from here to here is 60. Then from here to here is 70. So we have an overall concrete thickness of 130. Thickness of 130. So steel work and fire protection 0.3, ceiling 0.2. The total permanent load, permanent action is 3.4. Now, when you look at this load is in kilonewton meter squared, meaning that this load is an area load. So we want to convert this load to a linear load. So by so doing, we have to multiply the area load with the the bay width. So from here, when we multiply it, it gives us 9.7759, 9.775 kilonewton per meter. This is the linear load. So we also consider the variable action. So the variable action, according to this code, is 2.5. Then imposed floor load for movable partition. So we assume that there will be a movable partition, and that movable partition would not be less than 2.0 kilonewton per meter square. So we have this. So that is equivalent to 0.8 kilonewton per meter square. Then the total variable action on factor 3.3. Now, this load is an on factor load. This one also is on factor load. So the total on factor load for the UDL, for the variable action is 9.488. Then there is a clause in Eurocode 3 that recommends application of reduction factor application. Because of time, I might not, maybe I will show all the clause in a subsequent video. So we are going to apply the reduction factor of 0.92925. So when you apply this reduction factor of 0.925 on the GK and on the QK, then you now have this value for the GK and this value for the QK. So GK is the permanent action, QK is the variable action, which is imposed load. So here we don't have any point load from secondary bin, because what we are designing secondary bin. Okay, so we look at the ultimate limit state. So the partial factor for action. So for the GK, we have 1.35. For the QK, we have 1.5. So when you apply this partial factor of safety, you now have the design load at ultimate limit state to be 25.35. So this is the load that we are going to use for our design. This is the load that we are going to use for our design. Okay, so now design moment and shear force from beam max. Okay, so here we are going to calculate our maximum moment. We are going to calculate our maximum moment. Now, it is very simple for us to calculate our maximum moment. How are we going to do that? Whether we use this software or we can do it manually. Okay, but let's just do it manually. So here, our M max. Let's just calculate our M max. Our M max is going to be W L squared all over 8. So this will be 8. So let me quickly do this. So this will give us, so what is our W? This is our W. So we multiply it by this again. Then we divide it by 8. So we are gonna have, we are having this moment. That is what we have. So for this one, the maximum shear, so Vmax. So we look at our Vmax. Vmax is just WLX all over 2. let's all over 2. So this will give us divided by, okay, sorry, yes, times LX divided by 2. So this gives us K Newton. Okay, now, so let's go to this software and also analyze what we have here so that we know if this calculation is correct or not. So I'll quickly go to that software now so that we can just um, change the unit kilonewton meter. Then the length here is 8 meter. Then we have this. We have, so from here we apply the load uniform distributed. So the load is minus 25 minus 25.38. 25.38, no, 37, right? Let me check again. Yes, 37. 37. So we click OK. Okay, let's look at this again. Okay, okay, this should be, let me look at this. I think let me look at this. Oh, sorry. This was a huge mistake. Instead of 8, I used 2. Okay, I think that is fine. I would have said, oh, sorry about that. I used 2 instead of 8 because it's supposed to. I think that is correct. And check out this. It's the same thing. Let me see how I can. Let me see how I can. If you see this is about 202.3. But when you look at our own, it's 203, which does approximate this to 3. Then let's look at shear force. You can see here that the shear force is 101.5. Let's look at our own shear force here, 101.5. You see that this is correct. So here we can put this here and put this there. Okay. So we want to calculate the plastic, the required section to have a plastic modulus about the major axis. So this is what our design will require. So meaning that what we have here, or what we are going to provide will be higher than the required. So this is the required plastic modulus. This is the required design plastic modulus. So from here, this is what we use. So you multiply the the design moment or the applied moment by the yield strength of the steel, then partial factor for resistance, then all over the, okay, you multiply this by the partial factor for resistance, then all over the yield strength of the section. So we have this. So now that we are done with that, so we are going to pick a trial section. So the trial section that we are going to pick will be 406 by 178. 406 by 178 by 67 by 67. Okay. 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 So let's go to the steel section table 406 178. So let's go to the steel table. So this is 406 by 178. So we start with the depth of section. The depth of section. Here you have to be very careful so that you do not make mistake. So this the depth of section is 409.4. Depth of section, depth of cross section 409.4. 409.4. I have to cross check again. 409.4. Okay. So the width of section is 178.8. 178.8. 178.8. The width of section is 178.8. Am I correct? Let me go back and check. Yes, I'm correct. 178.8. Okay. So depth between fillet, D, depth between fillet, This is 360.4. 360.4. 360.4. 360.4. Now web thickness. So this is web thickness. Under this, web thickness is 8.8. 8.8. 8.8. 8.8. 8.8. So this will be 8.8. 8.8. Then flange thickness. Flange thickness is 14.4. Flange thickness is 14.4. 14.4. 14.4. 14.4. Flange, this is what we call flange. This is the flange. This is a flange thickness. This is a flange thickness. This is the web thickness. This is the web thickness. So when you check the web thickness is just 8.8. Then the flange thickness is 14.4. Then we look at the radius of root fillet, radius of root fillet, radius of root fillet, radius of root radius, root radius 10.2, 10.2. Okay, that one is okay. Now cross-sectional area, cross-sectional area for that. Cross-sectional area, we'll get it in the next sheet. Cross-sectional area. So we follow this. Okay, cross-sectional area 47867. Cross-sectional area 85.5. Okay, 85.5. Then we look at second modulus of area. 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 This is 24,300. 24,300. This will be 24,300. 24,300. So we look at second modulus of area on the z-axis. Z-axis. So this will be 1360. 1360. 1360. So 1360. 1360. Then elastic section modulus. Elastic section modulus. Section modulus. Elastic section modulus. So we go back again. Elastic section modulus. Elastic section modulus. We trace it. We have to trace it. Elastic section modulus. For this, elastic section modulus 119, 1190, 1190, 1190. Then plastic section modulus, plastic section modulus, plastic section modulus. So we plastic section modulus, plastic section modulus, plastic section modulus. We have this to be 1350. 1350. 1350. Okay, so this is what we have provided. This is a section that we have provided. So now let's look at, okay, so if you, from here you can know if that section will be okay or not. Because when you look at the plastic section modulus provided and the plastic section modulus required, you see that this is far higher than this. So this will tell you right from the initial, right from the trials, picking your trial section, if that section will be okay or not. So you can see here that the plastic section modulus provided is far higher than the plastic section modulus required. So it's just like, this is just like almost times 2. Let me check something. Let me divide this by this. About 2 point something percent. 2 point something. Okay, 1.829% higher. Okay, so fine. So let's start with the classification of cross section. Remember, in our previous video, we said that the bending moment resistance dependent on the classification of cross section. it depending on the classification of cross section. So in Eurocode 3 table 5.2 deal with the section classification. So it gives us this formula. Let me try and okay. So giving us this formula that mu is equal to this square root of 3,235 all over the yield strength of the steel, where the yield strength of the steel is equal to 275. So we are going to look at this table 5.2 and see where this formula. So when you check this, you will see that this will give us 0.92, and outstanding flange under uniform compression is equal to C, which is B minus um, thickness of web minus 2R all over 2 is 72.8 mm. So C all over TF, that is the thickness of flange, will give you 5.19. Now the limiting value for class 1 is equal to that. C all over T must be less or equal to 9 real. 9 real, which is, we already calculated this real here to be 0.9. Then we simply multiply this by 9, which which give us 8.3. So C is 5.19. C is a C over TF is equal to 5.19. So meaning that C is less or equal to this, which means that this section is class 1. So let's go to the code to confirm this. Let's go to the code, section classification, section classification. Okay. So this is class of section. So we have class 1. So class 1 for the roll section, this is where our design falls into. This is the section that our design falls into. Our section falls into roll section. So under class 1, C all over T must be less or equal to 9 row. So when you look at this, it satisfies this condition. So our cross section is class 1. But if it was C all over T less or equal to 10 row, then it would have been class 2. Okay, so this is how we arrive at this, and this is table 5.2. Table 5.2. So we continue with that design. So the first check has been achieved. So meaning that the cross section is class 1. The cross section is class 1. Okay, so therefore the flange outstand is in compression is class 1. Internal compression part web under pure bending. So we look at the C. C is equal to this. Then C all over T is equal to 3 point this all over 8 point, which give us this. So the limiting value for class 1 is C all over T less or equal to. Now, when you look at this, you see that the first one has been satisfied. Then we look at the second one, compression, flange outstanding compression is class 1. Then internal compression part. So we have to also look at the web under pure bending. The web under pure bending. So this is the thickness of the web. This is the thickness of the web. So the code says that C all over thickness of web is it must be less or equal to 72 real. So when you look at this, this is 40.95. less than 66. So therefore the web in pure bending is class 1. So you check the section classification, you also check the web under pure bending. So the pure bending here is class 1, therefore the section is class 1 under pure bending. Okay, so we are done with that. So we move to the next check. Which is member resistance verification. Now here we start with shear resistance. We start with resistance. So irrespective of the one that you start with, whether you start with the bending moment resistance or you start with the shear resistance verification. So it all depends on what you want. So here we start with the shear resistance. Now clause 6.2, 6.2.6, 6.2.6. Let's go back to this our material here. Let's go back to this our material. So you see here that clause 6.2.6 deal with the cross-sectional resistance for shear, which means that under this clause 6.62, we have equation 6.17. So this is the formula for it. So this is equation. We can call this equation. We can call this equation 6.17 under clause 6.6, under clause 6.26. Okay, so this is the equation. The applied shear all over the resisting shear, and it must be less or equal to 1. So here, how do we have, because already we have our applied shear. This is our applied shear. Let me show us our applied shear. Our applied shear is what we have already calculated. So this is our applied shear. So we have already calculated this. So this is the same thing as VAD. So anything in Eurocode that you see ED, that is applied. Anything that you see RD, that is resisting or resistant. So we have already gotten that applied shear. So here our duty is to calculate the resisting shear, which is under 6.2.6 section 2 of it. So this formula says that we have AV all over the yield strength all over square root of 3 all over this RMO, which is a factor for class 1. Remember that also that this one also depends on the cross-section classification. So for a row I section with shear parallel to the web, shear area is equal to this. So this is the shear area. Now, this AV must be less than this. It must not be greater than this. It must not be greater than this HW. Some of these things we lack name to call some of these symbols. This HW plus this. So let's see AV. How do we calculate AV? AV is A minus 2BV plus TW plus 2R into TF. Now, this is the cross-section area of the section. 2B is the flange 2B. The B is the flange width. The B, yes, the width of the cross-section. The width of the cross-section, which is this one. The width of the cross-section. Then plus TW, which is the thickness of the web, plus 2R. The R head is the root radius times the thickness of the flange, and must not be more than n this HW plus T. So we look at it. So this is the area of the cross section in millimeter times this times this plus 8.8, which is the thickness of the web times 2 root radius times the times the thickness of the flange. Yes, thickness of the flange. So we look at it. Thickness of the flange. Yes, the flange thickness. Yeah, the flange thickness. Okay, let me look at something here. Let's look at TW 2 BS times which is 2BS plus this one here is let me look at something here. Let's look at this material again. Okay, yes, 2B plus T plus 2R, yes, T, okay. So let me just do something here. Okay, plus T parallel to the web, yes. So let's look at this. Okay. So we have our AV. This is 2B. Okay. We are correct. Yes, this supposed to be T. And let me check this. B. This should be TF. Yes, we are correct. TF. So the B. So we are correct. Our formula is correct now. I think this is correct. I've been able to correct this. So we have this 3821. Then we calculate for NHW plus TW, which is N is equal to this is equal to 1 for conservative, 1 times 38 times this, which is 3349. So let's look at it. Now, the code says that whatever that you have, your AV should not be less than this one. So when you look at this is 3349, and what we have as our AV is 382, which is this one is greater than this. Therefore, AV is equal to this. So the design shear resistance is therefore. So we now calculate the design shear resistance. Now look at what we have. We have 606.7 kilometer. Then this is the applied resistance. This is the applied shear all over this, which is 0.17 less than 1. Therefore, the shear resistance of the section is adequate. Then we move to shear buckling of the unstable web. Now, shear buckling of the unstable web need not be considered provided that this HW, that is the, the height of the depth of the section, the depth of the section, web depth, the web depth is the web depth all over the thickness of web is less or equal to 72 all over n. So we calculate this and we have 43, then 72, we have this. Then since 43 is less than 66, therefore share buckling check need not consider. So we don't need to check for share or provide for share buckling. Need consider. Now, the next one is the moment resistance check. Now, the design moment is equal to applied moment all over resisting moment. And the code says that it must be less or equal to 1. So let's bring in the clause here. Let's bring in the clause here. So let's bring in the clause here. So the clause here is 6.6.6.25. 6.25, 6, we can put it here, 6.2.5, 6.2.5, 6.2.5, then equation 6.1 to equation 6.12. So let me just copy. There was a particular equation I wrote somewhere. Where is that? Okay. So this, let me copy this. This is okay. So this is equation 6.12. Okay, 6.12. 6.12. So this is how we calculate the resisting moment. This is how we calculate the resisting moment. So at this point, we have this plastic, section plastic modulus, which times the yield, section yield strength all over this factor. So at the point of maximum moment, the shear force is 0, yes. So this is the section plastic modulus 135 by, we multiply it by the section yield strength all over 1. So this now give us the 371 kilo Newton meter. This is the moment. This is the moment. Let me just copy this and move this to. So from there I can cut this, put it there. Then this is equal to the Newton meter. Okay, so the design bending resistance is 371. So when you check, you discover that the applied moment is 203, while the resisting moment is 371, which is far greater. So since 0.5 is less than this, therefore the bending resistance of the section is adequate. So you see those sections are okay. Then we move to the serviceability check. We move to the serviceability check. Physical deflection normally be calculated under the characteristic load combination due to the variable. So permanent load should be included. Permanent load should be included. So the characteristic load combination as a visibility limit state is given by this one. So the modified equation according to NA 2.2 to Eurocode 3 state that permanent load should not be included. So permanent load should not be included. So when we are checking for deflection of the beam, we use the variable action to check for it, and it should be on factor. So this is where we have this formula. This is where we have the formula. Now, if you go back to, let's go back to that our material. Let me show you something. Let me show you something. Okay. So now, because it is a UDL, so we are making use of this formula. We are making use of this formula. So here we just substitute it here with this is supposed to be W. This is supposed to be W. So we calculate this, and our small w give us this one. Then vertical deflection is span all over 360, which is 22. So let's check what do we have. 9 is less than 22. So therefore the vertical deflection of the section is adequate. So we can now say adopt. We can say adopt (406) by 178 still. So here we don't have any point load. So this is out, and this is out. So you can see here that our design is okay. So in our next model, we are going to demonstrate this same design using Autodesk robot structure, so that we can be sure we can compare the results of the two design methods. So thank you very much, and I believe that you have learned something. To see you in our next model. Bye.